Okay, let's start with homework assignment number 5, the second law of thermodynamics. Okay, problem number 1 is giving me that I have a cyclic machine, shown on the figure. I can draw the figure. The figure tells me that I have a reservoir, a high temperature reservoir at TH, and of course I have a low temperature reservoir, which is TL, and I tells me that I have a cyclic machine that works between those two reservoirs to give me work, and this of course QH, and that is QL, which is heat rejected. And then it gives me some numbers, like for example it tells me that TH, so TH is 1000 Kelvin, and it tells me that also TL is 400 Kelvin, and the work, yeah, and it also tells me that QH is 100, sorry, 325 kilojoule, and it tells me that QL is 125 kilojoule. And then it asks me if this is a reversible heat engine or irreversible or perpetual machine, which means that it's impossible. So the thing that I do is that first of all I need to find what is the Carnot cycle. So the Carnot cycle efficiency. We have learned that it's 1 minus TL divided by TH. Now, if you do so, then you get what is TL? Is now 1 minus 400 divided by 1000, and that's going to give you 60%, right? So for the Carnot cycle, the efficiency of Carnot cycle is 60%. Now I need to, what is the efficiency for the heat engine itself now? For the heat engine, it's the real one, because I have also data to check the real one. So the efficiency of, let's say, for real one, I don't know now, of course, if it's real or not, because it can be also equal to Carnot. If the efficiencies are equal here, it will be real and Carnot at the same time. But let's assume that this is what he claims, that it's real. And that's going to give you, it's again, it's the same, it's work divided by QH, because this is the definition of efficiency. And the work here, did I write? I didn't write the work here. I can write it here. The work is 200 kilojoule. So it's 200 divided by 325 QH. And this, if you do this, that's going to give you an efficiency of 0.615, which means that the efficiency is actually 61.5%. Now, if you compare between those two, you know now that it's the efficiency of the real one is larger than the efficiency of Carnot. And we know that cannot happen, because we know that according to what we have learned, according to Carnot, the best and the highest efficient heat engine that you can connect between those two reservoirs will have the efficiency of a Carnot. You cannot construct a real engine that hasn't or more efficient than Carnot efficiency. So this will be impossible, and I will write it by a different color so you know that this is important. It's impossible. So if somebody is telling you that I have done this machine, then you know that it's not correct. Okay, now to problem number 2. And problem number 2 is telling me that I have 2 kilograms of water, and those 2 kilograms executing a Carnot power cycle. Probably it should be 2 kilograms of water in a piston cylinder. Simply. So we know that it's a closed system, and that executes a Carnot cycle, and then start explaining to me during the isothermal expansion. So at the beginning of the cycle, the water is heated until saturated vapor, until it is saturated vapor from an initial state. So this is my state or state 1 in the Carnot cycle, and I go from this state 1, add heat until all the liquid or is converted into saturated vapor, and then when I come into saturated vapor, the expansion still continues, so I still expand, but this time adiabatically and not isothermally, down to a pressure of 1.5 bar while doing the work, which is 491.5 kilojoule per kilogram. So in a diabatic expansion, the work which I do in a diabatic expansion is 491 kilojoule. It's not strange that he's asked you now to sketch it on PV coordinates, because without sketching it now, it would be very difficult for you to construct the information that the problem is given. So I'll start with drawing it, just so we know. And because it's telling me a Carnot cycle, and I know much about Carnot cycle now, I know it's water, and what I need to do is that this is PV diagram, and it tells me that, okay, how do you know? We know that Carnot cycle comes between 2 pressures, and in this case you can see that it's the high pressure is 40 bar and the low pressure is 1.5 bar. And where can we start? We can start, I can do a different color. So it tells me that I started, the initial was, the pressure was 40 bar and the quality was 15. So my point 1 is here. And I added heat, so this is the isothermal expansion. So I added heat here until I reach to a point which everything is saturated vapor. So this is my actually point 2. So this is 1, this is 2, and then it's telling me that the expansion happen, or the next expansion is adiabatic expansion until the pressure is 1.1. So I will go sort of down here like this until the pressure is 1.5, and then we know from, I mean, you don't have so much information about the rest, but you know that in Carnot cycle you go back to 4, so that is 4. You have to complete the cycle, although you don't have information, or the problem is not giving you information for the whole thing, but it tells you that it's a Carnot cycle. So it undergoes, the whole system undergoes a cycle, and that is a Carnot cycle. And we know that Carnot cycle is like this. So this is expansion, followed by the adiabatic, and then it's expansion, followed by adiabatic expansion, and then it's followed by isothermal compression, and then it follows by adiabatic compression. Um, and if you draw, let's start with one. What do we know about one? Now, what we know about one now is we know that the pressure is 40 bar, and I also know that x1 is 15%. And I have two independent properties, which means that state 1 is actually fully defined. Let's look to state 2. Now, state 2, what do I know about state 2? I know that P2 is equal to 40 bar. I also know that T2 is equal to T1, but that won't help me so much because I mean, they are dependent. The pressure and temperature in this area under the dome is dependent, but I need two independent properties. And the independent property is that telling me the state. It tells me that it's saturated vapor, right? And this is why I can put this point here on the saturated vapor line. So 2 is also fully defined. All the properties here will be sort of the gas property. In this case, will be Vg that you can read from the table. So it is fully defined. Now 3, is it fully defined? It's not fully defined. I know that the pressure at 3 is equal to 1.5, but it's just one property, so I need another property to fix the point 3, and at point 4 it's the same. I also know that the pressure P4 is 1.5, but I don't know more. This is why I need another piece of information that can help me in fully defined state 3 and 4. And by defining the states fully here, I can calculate, of course, as you say, heat and work, and also thermal efficiency. So let's see what we are, how we can do this. Now, remember that this is a closed system, and you have drawn the diagram now, so that's going to help you sort of defining the processes. But I know that I need to go through all the processes. I can make it now in even different color. So this is Carnot cycle that I need to go through, and I can start with process 1 to 2. So process 1 to 2, what do I have? In process 1 to 2, I always start with writing the first law of thermodynamics. I think if you write the first law of thermodynamics and then you just try to check what kind of information that you know and what kind of information that you don't know. So if you take, this is divided by the mass, just so you don't have the mass, at least for this this stage. So Q divided work divided by the mass from 1 to 2, this equal to U2 minus U1, right? And now, what do I know? Now, state 1 is fully defined. This means that this one is defined, or I can find. U2 is also defined, because state 2 is fully defined. Now, do I know anything about Q? No. So I don't know this, and I don't know this. So I have two unknowns. So I need another equation that can help me in finding one of them at least. So this we can wait a little bit with. Now, I know that work or expansion work from 1 to 2 divided by the mass is equal to the integration from 1 to 2 pdv. That's we have learned, and we have done this many times before, and that's going to give you v2 minus v1, right? Now, let's say this can be 2. What do we know here? We know this, it's 40 bar, it's given, and we know v2 and v1 because, as I said, state 1 and state 2 is fully defined. We can even, this is one way, we can, if we combine 1 and 2, which means that if I say q1 minus 2 minus p v2 minus v1, that's equal to u2 minus u1. You can put this on mass, and even this can put it on mass, right? And if you do so, as you can see, you can even find q from 1 to 2 divided by the mass. That is h2 minus h1, just in this case. And please notice that if I sort of, if I don't want to sort of calculate this, the work for itself before, and then put it into the equation, I can always q, and that's also for, because the pressure here is constant. It's a constant pressure process. And this is why I can also do this. So either I calculate q from this, or I calculate the work from this, and then I put it here and I calculate q. It's, again, it's the same. And we can see what we are. So let's start with sort of calculating or getting some of the numbers from the tables. Now we know that, take this up. We know that from table A4 or A5, because pressure based, I know that A5 table, saturated table, I know that at P1 equals 40 bar and X1 is 15%, I can find V1, and V1 in this case equal to VF plus X VG minus VF. Now remember that this is the table that I'm dealing with. This is 40. I can read this is VF and this is VG, right? I have both of them. And X1 I already have as 15%. So if you put those two numbers, VG and VF, into this equation, you can find V1. And in this case, V1 going to be 0.00851 per kilogram. Now you can also find H1, and H1 it's the same, HF plus X HFG, right? And look to what we have here. So this is HF at the same pressure. This is HFG, so I have them here, and X1 is 15%. If you put those numbers here, you will get H1 as 1344.43 kilojoule per kilogram, right? So I can now calculate Q1 to 2 per mass is equal to H2 minus H1, and now I have H1 already, I need H2. How can we find H2? Now, H2 is actually Hg at P equal 40 bar. So, because I'm telling you, don't forget, we had from 1 to 2 was like this. We started 1 here, sorry, 1 was here, and then we heated until all the liquid became vapor. So we are on this line. So 2 is every property that at 2 that I need to find will be the G from the table. So if you go H2 will be Hg at the same at 40. So I can, if you do this calculation, you will find that H2 is 2814 kilojoule per kilogram. I read this from the table, of course. And to find Q, so Q1 to 2 divided by M in this case will equal to H2 minus H1. You already have, so this is H2 and this is H1. You put the numbers here and then you get Q as, of course you need to multiply this by the mass. Of course now you can multiply the mass here. So you get 2 kilogram multiplied by 2801.4 minus H1, which is 1344.43, and that's kilojoule per kilogram, and that's going to give you 2914 kilojoule, and that is Q1 to 2. Now I need to calculate the work 1 to 2. Now I can do either, because remember, we started writing the first law of thermodynamics as Q divided by M, or I can write Q 1 to 2 minus work 1 to 2 equal to the mass multiplied by U2 minus U1. This is where we started. So now either you know this, this is you have, and this is you have already calculated. So you can use this equation here to calculate work, or you can calculate the work by just, I can take some of this, or I can just take new one. So you can also calculate the work to equal to M multiplied by the pressure V2 minus V1, right? And remember, again, I will write it, I'll draw it so you know where we are. We started at 1 here, and we came at 2 here. So everything is, this is V1, this is V2. And remember, V2 is like VG. I read it from the table. So I can go here, and it's here. You can see this is, I just take it with me here and put it down here. And you can see that VG is already here, have it. And V1, how can I find V1? V1 I already calculated, so V1 equal to 0.00851, and V2 is actually VG at 40 bar. So I read it directly from the table, it's here. And now I know that work from 1 to 2 is mp v2 minus v1. P I know it's 40 bar, which is 40 of 4,000 kilopascal. I also know that this is 2 kilogram, and I know V2 and V1. If you put all the numbers here, you will get work from 1 to 2 is 330 kilojoule. And remember, this is positive. It's expansion work. So the work is done by the system and not on the system. Okay, let's try to do the process. So now is process 2 to 3. And I draw it here just in case that you this is 40, this is 1.5 bar. We started here, even a different color. We started here, this is 1, and then we came here, and then we went here, here. So this is 1, 2, 3, 4. And now I'm here. I'll take process 2 to 3. Process 2 to 3 is adiabatic. What does it mean? Adiabatic means that Q is equal to 0, delta Q. So there's no heat exchange. And that, if I write the first law of thermodynamics now, Q minus work, this is from 2 to 3, 2 to 3, this is equal to M U3 minus U2, right? And this one is 0, so the work is equal to the mass the mass multiplied by the change in the internal energy. And that, let's see what we have. Do we have the mass? We have U2, we have because 2 is fully defined. The work here, remember, it's given, and the only thing that I don't know is actually U3, and that's what I need to find. You're going to see why, because it's going to help you to, because as you remember when we started this problem, we said point 3 here is not actually fully defined. I just know that P3 is 1.5, but I don't have any other information that makes me fully defined. So I need to find another property, and that is U3. So the problem is telling me that this work here it's given as 400. If we go back here, just to show you the work here, you can see that the work in from 2 to 3 is 491.5 kilojoule kilogram. So we come here, and if we put it in, so this work so remember, if I need to find this, it's given as 491.5 kilojoule per kilogram. So to find the actual work, it has to be multiplied by 2 kilogram, because that's where you have the mass. That's going to give you 983 kilojoule. Okay. And from this, of course, I can find U3, because now I know that 491.5, this is the work divided by mass. So this is specific work. This is kilojoule per kilogram. This is equal to U3 minus U2, right? We know it from here. I just divided by the mass just to get rid of the mass, where then I can just deal with specific internal energy. Um, what is U2? Now U2 is UG at 100, I'm sorry, at P equal to 40 bar, because we are at T, and we said every property here is actually the property for the gas. So I can read it from the table. If I go here, UG, that is what I need. So this is UG, and this is UF, right? So U3, so U2, if I read this, I can write it down here now as, so 491.5 kilojoule per kilogram equal to U3 minus, now I know that this is UG at 40, and I know that this number is 262.36. And remember, this is kilojoule per kilogram, of course, kilojoule per kilogram. And if you do simple mathematics here, U3 will be 2110.8 kilojoule per kilogram. So now I have U3 and I have P3, which is 1.5. So I have two independent properties. So I actually can fully define the state, and I can take this and just put it here, and now I can find x3. Remember, I'll also draw here. See, every time I just start here, come here, then here, then here, then here. This is 3, 4, 1, 2. So now I'm trying to fix this, and I want to find x3. So I can calculate other properties that I need. And to find x3, we can just do, I mean, we know that x3 is equal u3 minus uf divided by ufg. And everything here at p equal 1.5. So I go here, this is a table, and I read uf, this is uf, so I put it here, and then I read ufg, this is, it's not here, but ufg is actually ug minus uf, and this is ug here. I take hf. This is of course not right. This is uf, and this is ug. And put those numbers here. And u3 we already found in the previous slides. If you put them all these things together, you will get that x3 is equal to 0.8 1. So that x3. And now x3 can help me, of course, to find h3 and v3. So h3 in this case, of course, it will be hf plus x3. Now I know hg minus hf. And I have all of them. This is from the table. They are here. This is hf. And this is hfg. So if you do this, you will find that H3 I yeah, I don't have it here at least, but you can at least find H3 here. I'll see if I have the number later. And you can also find V3, because V3 is Vf plus X Vfg, or Vg minus Vf. And those also you can read from here. You can see this is Vg and this is Vf. And that's going to give you V3, right? So now we have the work and we have the Q for process 2 to 3. So now we start with process 3 to 4. We start here, and again I also need to draw this is the process that I have, and this is PV, and we started somewhere here. No, started here one, then we went here, and then here, here. So this is 1, 2, 3, 4, and now we're dealing with process 3 to 4. So process 3 to 4, what do we know? It's actually similar to process from 1 to 2, but now it's, of course, compression rather than expansion. But the work 3 to 4 is P V4 minus V3. So this is how I can calculate the work. And Q 3 to 4, now we know it, is H4 minus H3. I don't want to go in detail now on this because it's the same as what we've done last time. And just to check what I know and what I don't know. Now, the problem with this here is that I don't know this. I want to calculate this. I know this. I don't know state 4 yet. I know this. So I have two unknowns. And if you look to here, I don't know this, and I don't know this, and I know this. So I still have also two unknowns. So I have three unknowns here with two equations. I need an equation, another equation. And this equation I can use from the absolute temperature scale. And absolute temperature scale in chapter 6 told me that if you have two reservoir, if you have two high temperature and low temperature reservoir, Q 3 to 4 divided by Q from 1 to 2, and you know it more because this is QL and this is QH. So QL divided by QH equal to TL divided by TH, right? I can write it a little bit. So QL divided by T by QH is actually TL divided by TH. Now, I know this, and I know this. It's saturated temperature at 40 bar, and this is saturated temperature at 1.5 bar, because this is where you have. And QH I already calculated, because you should remember that QH is actually Q from 1 to 2. So I have already calculated this. Then I can find QL, right? So that's, now I have three equations with three unknowns. That, of course, would be easy to calculate. So Q 3 to 4 is actually 384, just I'm putting some numbers here, divided by 523.4, and that is multiplied by 2914. This is Q. So this is temperatures in Kelvin, as you see, and this here is QH. This is QL, and this is I'm sorry, this is TL, and this is TH, right? And that's going to give you QL, or Q rejected, as 1070.1 kilojoule per kilogram, right? You have to define by the mass here, remember, because this is by the mass again. And I do this because I want to find, because Q 3 to 4 divided by the mass, as you can see here, is the same as to say H4 minus H3, which means I know this now, and I know this, I can find H4, right? And why do I need to find H4? I need to find H4 because I need to, this state here is not fully defined. I need to find X4, or the quality at 4. And I can do this. First I need to find H4. So H4 is actually H3 minus this Q3 to 4 divided by M. And that's going to give you 2 to 50.5 minus 70.1, and that's going to give you 1180 kilojoule per kilogram. That's 0.4. Okay, so what do I know now? I know that H4 I know now H4 is 1180.4 kilojoule per kilogram, and I can now calculate X4, because what is X4? Now X4 is equal to H4 minus HF divided by HFG at P equal 1.5. So I can go here and just copy just to use it here. And you can see what he's telling me is that to find H4 or to find X4, H4 is already, we know, already calculated. HF, it's here. I can just bring it from here. And HFG is from here. So I have this number, and I have also H4 as 1180.4 kilojoule per kilogram, and that's going to give me X4. If you put all these numbers, I can even write it 80.4 minus 467.1 divided by 2 to can read it here, 226 oh 2226.5, and if you do so, you're going to get X as 32%. I can write like this. Okay, so now I know X4, which means that I can find any property that I want at point 4. And what do I need? Remember, to calculate the work, you need to have, so the work from 3 to 4 is actually PM, or MP, multiplied by V4 minus V3. V3 I already have. This is I have, and this one I have. I need V4, but V4 I can find because I have X4 now. So V4 is equal to, because you have X4, yes, V4 equal to X VF plus 1 minus X VG at, so this is VF, this is VG, and if you do this, you're going to get V4 as 0.373 meter cube per kilojoule. And U4, you will also need it. Do the same, X UF plus 1 minus X UG, and if you do so, you're going to get this is as 3.8 kilojoule per kilogram. Going very fast now because most of you have control over these things, or dealing with tables. And now you can calculate the work. So first you can calculate Q 3 to 4, just 2 kilogram, which is the mass multiplied by H3 minus H4, and that's going to give you minus 2140.2 kilojoule. And you can find the work from 3 to 4 is the mass multiplied by P multiplied by V3 or V4. Depends on that you understand this is a minus work. It's a compression work. Minus V4. If you do so, you're going to go this minus 167.1 kilojoule. Okay. We can now try to go to problem or process 4.1 now, because again I can draw it here, just we keep track of things. .40 bar, this is 1.5, started somewhere here, went here, then down here, 1, 2, 3, 4, and now this is my process from 4 to 1. It's adiabatic, so I can write, you can see that the adiabatic process is easier. So process 4 to 1, Q 4 to 1 equal to 0 because adiabatic compression. And work for 1 divided by mass is equal to U4 minus U1. U4 I have and U1 I have already because it's fully defined. So just put the number. Minus. And U1, I didn't calculate U1, but you know that U1 is, oh, I need to do this. This is here is 1. I know X1 is equal 15%, and I know also that P1 is equal 40 bar. So I want to go to the table first, just to bring it at 40 bar. This is the table. So if we bring the table here, you can see that to find U1, I have X and I have also the pressure. So this is the pressure. So I read UF and UG, and so U1 will equal to X UF plus 1 minus X UG. And if you do so, I can write it down here. It's going to be something like 2.3. It's UF plus X the UFG. So you can also do U1 is equal to UF plus X1 UFG if you have UFG. It's the same, this one or this one. And that's going to give you, so X1 is 0.15 multiplied by UFG, which is 1520. So this is 1520.0. And if you do so, you're going to get the work divided by the mass for specific work is 186.5 kilojoule per kilogram. So if you multiply this by 2 kilos, it's going to give you the total work, and the total work would be minus 373 kilojoule. Okay, now he also asked to find the thermal efficiency, and the thermal efficiency in this case is, let's try to find the thermal efficiency. Now the thermal efficiency can be found in two ways. One of them is that you just take the work of the cycle, and now I'm talking about the net work net of cycle, divided by Q in into the cycle, which is, I can write Q in is the one that Q from 1 to 2, right? And the work of the cycle, I can also again draw this here. This is my cycle, 1, 2, 3, 4. And I have done work here, I have done work here, I have done work here, and I have done work here. Two are positive, so this is positive expansion, and the other portion I can do with a different color, so we know this, that from here to here, this is compression, and from 1, 2, 3 is expansion. So if you want to do now the net or summation, is actually the summation of all of them with the signs. So this is positive plus 983, this is also positive, minus 167.1 minus 373. So this is a compression, this is a compression, and the other one here is expansion. And thanks God that you see the summation of this is larger than summation of this. Otherwise it wouldn't make sense to have the whole thing. Divided by Q in. And this is just Q in, of course, is 2914.0 already we've calculated. If you do so, you're going to find that this will result in, which is 26.5% efficiency. You can also use the temperature, so using temperature, you can see this is a Carnot cycle, so it's going to give you the maximum. That's T cold or TL divided by TH, and that's 1 minus 384.4 divided by 523.4. If you do so, you're also going to get the same results, and that's going to give you 26.6% of efficiency or thermal efficiency for the whole cycle.